Today, I'm going to be talking about solar power. I hope everyone can hear me okay, as I sit in the middle of the crowd instead of at the front. But so I kind of have three things that I kind of would like to talk about. So kind of as an overview of what I would like to be talking about today. First, a kind of somewhat overview, but somewhat in-depth explanation of solar energy. I'm guessing it's a rather broad crowd in terms of knowledge, and so hopefully this gets everybody at least on the same page. And then I'm going to talk about two specific problems with solar energy. One of those is the cost. Turns out solar energy is extremely expensive. And the other problem that I'm going to discuss briefly is how we can actually store the energy, because as everyone knows, the sun is out during the day, and that's not usually when we need electricity for things like lights. And so how do we solve this problem, or how do we address this problem? So first of all, a brief overview of solar energy and kind of why we might want to use solar energy, what are the problems with solar energy, and an overview of how solar cells work. So first I'd like to, before I even start talking about solar energy or how solar cells work, I'd kind of like to talk about why we might be interested in solar energy, or get an idea of what kind of problems there are in the world just with power in general. And to discuss any problems with power, understanding how much gas we need, understanding how much coal we need, stuff like that, we kind of have to understand how big the problem is before we can address the problem. And so I'm going to go through a few slides to kind of hopefully get everyone thinking about how big of a problem this is, how much energy we use every day, or how much power we're using at any given moment in time. So I'm guessing most people have cell phones. I'm going to also guess the vast majority of people in here have a better cell phone than me. Turns out a cell phone uses about 1 watt of power. At any one time, it's using about 1 watt of power. If I were to take 1,000 cell phones, I would have 1 kilowatt, which is about the power output of your average household toaster. This is also about how much power your house is using at any given point in time. At some points it's higher, some points it's lower, but on average, your house is using about 1 kilowatt of power. If I were to multiply that by 1,000 times, I would get to a megawatt. And a megawatt is the power output of a standard, just common turbine engine. So a turbine engine that you would find on a jet plane has about as much power as 1,000 houses or 1,000 toasters. If we're to multiply that by 1,000, we're up to a gigawatt. So this would be 1 billion cell phones, for instance, would be 1 gigawatt. A gigawatt is the power output of a kind of small nuclear power station. But this is about how much power a lot of smaller power stations put out. It's about a gigawatt. If we're to multiply that by 1,000, we would be to a terawatt. And in this picture, I'm just showing all the lights of the world lit up. So a composite image of night everywhere on planet Earth. All those lights constitutes about 1 terawatt. And on planet Earth, we need about 15 terawatts. So we use about 15 terawatts at any given time. So that's a lot of power. When you think about a power station needing 1,000 power stations just for 1 terawatt, we need about 15,000 power stations, 15,000 nuclear power stations, for instance, to power the world. And so that kind of hopefully gives you some idea of how big this problem is, how much energy we use as humans on this planet. And you also need to take into account that the vast majority of the planet does not use power like Americans do. It turns out Americans use the vast majority of the power on planet Earth. And other countries are quickly catching up. For instance, China and India are quickly catching up in their power needs and power uses. So this 15 terawatts number I have here is going to become outdated rather quickly. So where does all of our energy come from? Right now, the vast, vast majority of it comes from 3 places: either oil, coal, or gas. As you can see here, about 37% is from oil, about 25% is coal, and about 23% is gas. This is across the world. So it's a little bit different from country to country. For instance, in America, we use a little bit more coal than a lot of places because we have a lot of coal to use for electricity. Other places use more natural gas or use more oil, but the overall factor is about the same everywhere.
Excuse me, you were switching from electricity, now you're switching to all energy?
So when I say here 15 terawatts, this is all power. So this isn't just electricity. This is transportation, for instance. So that 15 terawatts is everything. And that's wrong way. Yeah, that's what I'm taking into account here. So a lot of this is electricity. Most of it's electricity, but we also have to worry about things like heating homes, car, fuel, transportation, stuff like that. So most of it, 85% comes from oil, coal, and gas. And I'm not going to tell you all the problems with oil, coal, and gas. There are people who have ideas of what some problems are. Some people disagree with that. Some people think there are other problems. The vast majority of people, though, do want to get away from oil, coal, and gas. For instance, in this country, we'd really like to get away from oil for a number of reasons. Whether you think it's global warming, whether you think it's security reasons, terrorism, you can come up with a whole broad range of reasons to get away from these three things right here. A lot of people also think we're running out, especially of oil. Coal, not so much. But oil and gas, a lot of people think we're running out of. And so there's a big push to get away from these three energy sources. So the question is, if we're going to replace 85% of our energy, where is that energy going to come from? So the thing to do is look at where, what's filling up the gap right now. If we look at this breakdown of every place else we get energy from, the biggest portion in the world is nuclear energy. We don't get a lot of that in this country, but around the world, there's a lot of nuclear energy. That's followed by biomass. Biomass is predominantly used for heating, so chopping down trees and heating homes or cooking. This is done the majority of this is done in a non-sustainable manner, so we're chopping down trees faster than the trees will grow. Hydroelectric, so dams. Solar heat is about 0.5% of our energy, and it keeps getting smaller. Wind. You'll notice, hopefully, if you can see, solar photovoltaic is an extremely small. It's basically not even a drop in the bucket, 0.04%. That is, 4 cents for every dollar, essentially. Or actually, that would be 4 cents for every $100. Yeah, 4 cents for every $100 is solar photovoltaic. And so there's a lot of room for growth in solar photovoltaic. Not a lot of people are using it. So let's go through each of these, talk about their pluses and minuses, just real quickly to kind of understand, if they can even meet the demand. So first off is nuclear. Turns out worldwide there are about 440 plants. This is a little outdated. I think it's up to about 450 now, but that doesn't take into account China, which just lost a couple. Around the world, there are about 300 under construction, and about 100 are in the planning stages. However, if we want to replace all the oil and the coal and the gas in the world, we'll need to build 15,000 reactors in the next 40 years. That's more than one per day. And if we can't even build 30 in a few years, there's no way we're going to build one per day. There are also other problems with nuclear reactors, and most of those are here. For instance, there's a very high front-end cost to nuclear reactors. They're very expensive to build. Once they're up and running, they're pretty cheap and efficient, but to actually build them from the ground up becomes very expensive. Issues of security. Issues of nobody wants them around. Everybody wants the electricity, but no one wants them nearby. Supply, how much uranium is there in the world, things like that. And so there are a lot of problems with nuclear. It can fill in a lot of the gap, it can help out a lot, but it's not going to replace oil, coal, and gas anytime soon. The next is biomass and biofuel. So for instance, chopping down trees to do cooking, for instance. There are a lot of people who want to use ethanol or switchgrass, corn ethanol or switchgrass ethanol for fueling cars, things like that. Problem with this is that it is fundamentally inefficient, or at least one of the biggest problems with biomaterials is that they're fundamentally inefficient. The purpose of biological things is not to provide us energy, but to stay alive. So most trees and plants are interested in staying alive. They expend most of their energy trying to stay alive. So that's not a lot of energy left over for us to harvest and turn it into things like electricity or fuel. However, it's still possible if we were to coat 30% of Earth with things like switchgrass, we would be able to get about 20 terawatts out. However, the vast majority of this 30% is not land that you can grow things on. So if we were to actually take all of the available land in the country or in the world, and so that's things like land where people aren't living, land that's not in Antarctica, land that doesn't have food crops growing on it, we would be able to get about 5 terawatts out. And so it can make an impact, it can make a difference, especially if we can fix this 1% part. There are a lot of scientists in the world working on that. But as of right now, it's not going to be able to replace oil, coal, or gas, although it can make a significant impact. Next is hydroelectric, which is basically just putting dams in rivers. If we were to dam every stream, river, and brook on the planet Earth, that would yield about 4.6 terawatts. The majority of that, though, we can't get to, or it's just not feasible technologically. The water's moving too slow to really get an efficient dam. If we put it every place technologically feasible, we can get about 1.5 terawatts out. That becomes expensive. If we just worry about the places that we have the technology for and we can actually get to, and it's not cost prohibitive, we can get about 1 terawatt out. But already we're getting about half of that. And so the vast majority of places we can put a dam, we've already put a dam. So that's one of the biggest things with hydroelectric. It's an excellent source of energy, but we're getting about as much out of it as we can already. The next is wind. Turns out that there's a fair amount of wind energy in the world. Again, I don't have it up there, but there are 2 problems with wind. One of those is that we're already getting a lot of energy from wind that we can, at least on land. There's a lot that we can get offshore that we're not taking advantage of, but currently most of the energy that's on land that we can take advantage of, we are. 2 problems with this, though. One, windmills tend to be expensive. They tend to be mechanically unreliable. They break down quite a bit. Anyone who's ever driven from here to the Bay Area over Altamont Pass has probably seen a number of windmills that aren't turning. A lot of times they just need a lot of work and repaired because the mechanism behind them, the internal mechanisms, don't work as well as they should. Well, they work about as well as they can, but it'd be nice if they worked better. And the other problem is you can only put so many windmills in one place. As they get closer and closer, the wind stops pushing all the windmills, and so you can't get a high enough density of windmills, at least with current technology, to get this much energy out. Solar, on the other hand, is an incredible energy source, especially considering that we're only taking 0.04% of it, at least photovoltaically. So at any given point in time, there's about 120,000 terawatts coming from the sun reaching the surface of planet Earth. Remember that humans use about 15 terawatts of power at any one time. And so there is a huge excess of power coming from the sun. In fact, from the sun, we get more energy in 1 hour than we use in 1 year in terms of energy. So there's just an incredible excess of energy coming from the sun to planet Earth. Unfortunately, we don't have a good way of harvesting that right now. And so of all the alternative power supplies, solar really does have the potential to completely replace oil, coal, gas, all of these carbon, non-renewable sources, with room to spare, but we aren't able to do it yet. So just kind of as a comparison, if we were to coat this much area of land with modern solar cells that are about 20% efficient, we would generate about 3 terawatts, which is about the energy need, or about the energy need of the United States. While this looks like a lot of land, this land area is comparable to the highways in the United States. So if every freeway, not every highway, every freeway in the United States was coated with 20% efficient solar cells, we would generate about as much energy as we need in the US. And so what's the problem? Why haven't we done this? I make it sound very straightforward, very easy, and oh, it's so awesome. Why don't we